When you travel in a blood vessel away from the heart and the systemic circuit, there's a predictable series of vessels that you're going to encounter. Elastic arteries, muscular arteries, arterioles, and then I have capillaries at the very end, but capillaries are really, they're not arteries or veins, they're their own category. So as you travel from the heart to the capillaries, the diameter of the vessel gets smaller. You can see that on the left. But there's also some other structural changes to that artery wall. Most noticeably, there's less smooth muscle of the tunica media. There are also fewer and fewer elastic fibers until there are ultimately none in a capillary. Elastic arteries have an incredibly thick wall to them, right? And this thickness of the wall is capable of preventing blowouts, even though this artery is subjected to 120 millimeters of mercury of pressure, which is actually a lot for a little vessel. Elastic arteries, they don't want to have a blowout or an aneurysm, which is why they have such a thick wall. You cannot constrict these arteries, which is kind of strange, right? Because like, why is there so much muscle here if I can't even use it? They won't constriction of an elastic artery, it won't reduce the diameter of the lumen, but it will maintain the diameter of the lumen. So they'll construct to control, so they work to control the shape, maybe not change the shape. These vessels, elastic arteries, they recoil a lot and then fill again, recoil a lot and fill again. And as these vessels rebound, they push back against the heart. And remember, there's a valve in the heart called the aortic valve, which controls blood leaving the heart to the systemic circuit. Elastic arteries, like your aorta, they push back on your aortic valve for a split second, and that's what's called afterload. It's that pushback. You can also see in this artery, this purple line right here, and then this purple line right here. These are the elastic lamina. So even though there are little elastic squiggles throughout the smooth muscle, there are kind of these two sheets of elastic tissue. As you travel from the heart and the systemic circuit, elastic arteries, they transition to become muscular arteries. And I didn't say this, but elastic arteries can be called conducting arteries because they conduct blood to very general regions of the body. These arteries here, muscular arteries, can be referred to as distributing arteries because they distribute blood to specific organs, not general regions. The renal artery that comes off the aorta and brings blood to the kidney, that's a distributing artery. During exercise, muscular arteries and arterioles, they can redirect blood away from the stomach and digestive system, ensuring that resources are directed to your active exercising muscles. The term muscular artery refers to the very, very thick amount of tunica media that you have in these muscular arteries. They too have an internal and external elastic lamina. However, they're much thinner in thickness, and many times the elastic lamina on the outside isn't even present. I want to mention also, you can see the internal elastic lamina here. It's actually hiding behind the simple squamous cells lining this vessel, but it's that squiggly line right there. As we travel even further away from the heart, the muscular arteries transition into arterioles. These vessels, which are also called resistance vessels, have a relatively thin tunica media compared to its diameter. The diameter is small, so small that you could see the red blood cells in the lumen and count them. In muscular arteries, you can see individual red blood cells, but there are usually too many to really realistically count them. And in elastic arteries, all you really see is just a pink glob for the red blood cells. On this picture on the left, I have an arteriole with its corresponding vein. And on the picture on the right, it shows an arteriole with a very darkly stained elastic fibers that are just superficial to that simple squamous cells that line the lumen. Arterioles control blood pressure, and this picture explains how arterioles provide the most resistance for blood flow and are therefore the greatest determinants of blood pressure. On the left side of this capillary bed is an arteriole wrapped with some smooth muscle, and it's controlling the flow into this capillary bed. On the right side, of course, is the venule that drains the capillary bed and provides very little resistance because we know that veins and venules are always a little bit bigger than their corresponding arterioles. So, shown here are many capillaries that are fed by one arteriole. And this reminds me of skiing in the 1980s with my mom. I don't know how things are done now. I have no idea. But back in the 80s, everybody would get in one line to get to a ski lift. And as you got closer and closer to the lift, then you started to get sorted into individual lines by the number of people in your group. So if you were one person, you went this way. If you were two, you went in this line. If you were three, you went over there in that line. But it was still a situation where one big line of skiers was feeding into many smaller lines. And this is the same situation with an arteriole. One arteriole can feed many capillaries. And compared to the number of capillaries, the number of arterioles in your body is quite small. And this is why arterioles are like a bottleneck to flow and provide the resistance that determines our blood pressure.